So this is a summary of how to do a QR decomposition with the Hausdorff transformation. So if you have your matrix A, let's call it A node, so this is 0 here. The key part for the Hausdorff transformation that you need to remember is first, of course, the formula. So that the Hausdorff transformation is equal to the identity matrix minus 2 times U transpose over U transpose U. That's really, first you need, of course, to remember the formula. The other key part is you need to remember that each time, for each step, you need to consider the submatrix, the first time the entire matrix and each time a submatrix. So here the entire matrix is in yellow, then this kind of brown here, then this red brown here, then you continue until you reach a 2x2 submatrix. So really the key part is you each time consider a submatrix, and you consider especially the first column vector of this submatrix. So in the first case, if you consider the entire matrix, you consider the first column vector of the entire matrix. Then you consider the submatrix, and as said, you consider the first column vector of this submatrix here. So in the first case, if you consider the first submatrix, you will only have one vector, one element of the entire column vector that is not inside this column vector in the submatrix. And then the second time you will have two elements that won't be inside, so that you won't consider. And so you will consider the first column vector of this submatrix, and then you continue until you get a 2x2 submatrix. Okay, here this is the step. These three dots here, they show that we continue until we reach this 2x2 size. Okay, of course, if you first have a 3x3 matrix and a 2x2 matrix, you don't have those extra steps because n is very small. But if n is very large, you do that. Okay, by that I mean that if you only have to deal with 2x2 matrices, you don't need to consider these submatrices because there is no submatrices inside that you need to consider. And if you have a 3x3 matrix, you won't consider 3 times or 4 times the submatrix because there's only one submatrix inside. That's all what I mean. But for larger n, you need to deal with that. Each time you consider the submatrix and the first column vector inside the submatrix. Okay, so first you will have an n by n submatrix, which will be the entire matrix basically. Then the n minus 1 by n minus 1 submatrix, and the n minus 2 by n minus 2 submatrix until you reach this 2x2 submatrix. And so now again for the formula, remember that there is a 2 here, a negative sign here, and that the first is U transpose U here in the denominator. That is simply the dot product. Remember that is simply the dot product written in matrix notation. And we need to divide this U transpose here by this dot product because we need that the result be normalized, okay, that it is of length 1. We need it once for this U here and this U transpose here. That's why we divide it, because remember that the dot product is equal to the dot product is equal to the norm squared. Okay, so you have it 2 times in the denominator, and so we can divide each U by this by its norm. Then remember that this U transpose in the nominator, so above the fraction part, this U transpose is simply a matrix multiplication, nothing complicated. That our vector U is defined as x minus x prime, where x is, as I said, each time this first column vector of the submatrix we consider. Okay, so I've written here with the same colors than here. So first, of course, if you consider the entire matrix, the U vector x is the entire column vector of entire first column vector of this matrix. Then the second time is the first column vector of this submatrix, this n minus 1 by n minus 1 submatrix, and so on. Okay, each time until you reach again this 2x2 matrix. This will be the first column vector of this. It will be the first column vector of this 2x2 submatrix. So again, this right here. That is your vector x. And remember that in total you begin with x sub 1, x sub 2, x sub 3 until you reach x sub n minus 1. You don't go until n because n would be the last column. And the last column we don't touch it because remember that for an upper triangle matrix you do it like that. And the last element, we don't need to kill him. Here it could be everything. Here we have 0, but the last column we don't need to touch it. So we only have x n minus 1 times this. We only need to find n minus 1 times this this first column vector. And also remember that this x prime is has its first component the norm of this first column vector, and all other elements are 0. Remember that. So that means again that so for the x prime sub 1, x sub 1 prime, well, basically the first column, the first element of this column vector will be the norm of this vector x1, so the norm of this first column vector, and all other elements will be 0, and this is the same for x sub 2 prime, x sub 3 prime, until you reach this x sub n minus 1 prime. Each time the first element is the norm, the other elements are 0. And for the last, here we only have 1, 0, because remember that it is a 2 by 2 submatrix, the last submatrix, and so of course vector here only has 2 dimensions. So the first will, as said, be because it is the first element, it will be the norm, and the other one will be 0. Now, so you find each time your vector u, which is okay, u sub 1. So your first vector u is this x sub 1 minus x sub 1 prime. So as said, you compute as said here. Then you find all your vectors u for each step. Again, each time the vector u will have one less element because you consider only a submatrix of this entire matrix. Okay? The first time you consider the entire matrix, so u has n elements. The second time u sub 2 would have n minus 1 elements, and u sub n minus 1 again would only have 2 elements, as said. Yes. Now for your matrices, each time you find your Hausdorff matrix. Again, your identity matrix, you also need to be careful that each time it only has the dimensions of the submatrix. Remember that, okay? The first time, of course, it is the entire matrix, so your identity matrix will have is an n by n matrix, but the last time it will be a 2 by 2 matrix, because again we consider this last submatrix here. And of course, if you plug in everything, as said at the first time, your Hausdorff transformation will have the exact same amount of dimensions as your matrix A, because we consider it the first, the entire matrix. But from the second time until the last time, your Hausdorff transformation won't have the same amount of dimensions, and so you need to put ones in the diagonals and 0 elsewhere in order to match again. Okay, the first time you will have an n minus 1 by n minus 1 submatrix. So you will plug in your Hausdorff transformations in those lower dimensions inside at the place of this submatrix here. So this first submatrix, and then as you will fill a 1 in the diagonal and 0 elsewhere. The second time you will have n minus 2 by n minus 2 submatrix. So again you will plug in your Hausdorff matrix that you found in those lower dimensions here in the place of this submatrix, and you will put 2 ones because we need to go to n, and if you have an n minus 2 by n minus 2 submatrix, we need to have 2 more dimensions. So we put, again, I said, 2 ones in the diagonal here and 0 elsewhere, so that the dimensions matches again. And the last time, if you have our 2 by 2 Hausdorff matrix, so the last step, we will put n minus 2 ones in the diagonal, okay, because we only have 2 dimensions, and to go to n we need to add n minus 2, okay, n minus 2 plus 2 is n, and we have again the same amount of dimensions, so we will put n minus 2 ones in the diagonal, and of course 0 elsewhere. And yeah, so I really hope it is clear. So we do that only so we can multiply our Hausdorff matrix with A each time, and each time you multiply with A, then what happens? Well, you will get 0 in the column vector that you considered. So the first time you will get 0 everywhere in the first column vector except the first element, that will be the norm of the old vector. Second time here, the fact that you put the ones in the diagonal outside of the submatrix will ensure that everything you did outside the submatrix won't change once you multiply a second time. That is the goal also of these ones and zeros. They basically act like an identity matrix outside the submatrix. Remember that the identity matrix, if you multiply it with whatever matrix you have, it doesn't change anything. That's why we put ones and not something else in the diagonal and zero elsewhere. Okay, so the second time you will, so I said everything outside won't change. That means that as said in the first column vector you will have zeros everywhere except in the first place where we will again, as said as before, have the norm of the old vector. And that you don't forget it, write this part here, this part here, that the upper right corner, it doesn't need to be zero. We only need to have the zeros below the diagonal. That's obvious maybe for you, but I just want to recall it. Remember that you only need zeros below the diagonal and not above. So here we have the norm of this vector. If you have zeros, here we have our submatrix, but the elements here in the top right corner that you will add, they can be whatever you want. They can be zero, but they don't need to be zero. So coming back before, the second time you multiply, we will have zeros here in this second column vector, the column vector inside this first submatrix, and the first element of the first column vector of this first submatrix will be, as said, the norm of this first column vector inside this submatrix, the old column vector that we considered here. And so the third time you will have again everything outside the submatrix didn't change. Okay, the x sub 1 and x sub 2 didn't change. I mean, we still have 0 here, we have some stuff here, and we have still the norm here of the old column vector. And again, for after the first transformation, in your third column vector, the first column vector of the submatrix will have 0 everywhere except in the first place, where we will have the norm of the old first column vector of this submatrix. And again, then you proceed until you reach this 2x2 submatrix. And where was I? Yeah, once you reach that, so you will need n-1 transformations, because remember you need one transformation for each column vector except for the last one that we don't need to touch, because remember we don't need to touch it to get the upper triangle matrix. So you will do n-1 transformations. It is also written here, and at the end you will have in the diagonal you will have the norms of the old column vectors of those submatrices, and 0 below the diagonal, and everything in the upper right corner. I mean, above the diagonal, basically. It can be anything. We don't care about it. And remember that this is true except for the last column vector. I said again that we didn't touch, and so it can be anything. We don't care about it. Of course, it will be affected by all those transformations that we applied to our matrix A successively, but those are indirect results. It wasn't planned that those numbers change however they change. It's just indirect. We don't need to touch the last column vector. And so again, if we apply all our transformations, we will get our upper triangle matrix R. And again, as said in the last videos, remember that A is equal to QR. Q is orthogonal, so its inverse is equal to its transpose. So we can multiply by Q transpose. So Q transpose Q here will give us the identity matrix, so we don't care. And we will get Q transpose A is equal to R. And so Q transpose will be equal to all those Hausdorff transformations applied to A. I don't know. Sorry, this A is not part of that. Okay. Yes. So because remember, if we apply all our Hausdorff transformations, we get an R, And so we know that Q transpose A is also equal to R, so Q transpose should be equal to all those the product of all those Householder transformations. So yeah, from right to left, h sub 1, h sub 2 until h sub n minus 2 times h sub n minus 1. Okay, remember we only have n minus n transformations because the last column vector we don't touch it. And so yeah, you can take the transpose. Q is equal to the product of all those Householder transformations transposed. And remember that the transpose of A times B is equal to B transpose times A transpose, or A transpose times B transpose from right to left. And so here's the same thing. You could write it out, this H sub n minus 1 until H sub 1 transpose. You could write it out as a H sub 1 transpose, H sub 2 transpose times blah 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 until H sub n minus 1 transpose. H sub n minus 1 transpose. Okay. Yes, and so remember, all we did is simple geometry. We each time consider a column vector, be it the entire column vector or the column vector inside the submatrix, it doesn't matter. And what we do is we reflect this column vector in such a way that it reflects across a hyperplane that, again, we don't really care about. This is simply the theoretical explanation, but we don't need to do anything with this hyperplane. We don't need to find it, we don't need to calculate it or whatever. It's just the theoretical background. We reflect it in such a way that we choose the hyperplane in such a way that its reflection lies on a coordinate axis, which will be, again, I said, the first dimension in the submatrix that we consider. So that the first time it will be the first element, then the second, third, and so on. That's what I mean. That the first element of it will be this coordinate axis is the coordinate axis of the first element of the column vector inside the submatrix. I hope it makes sense. That is, it's always in the first place of this column vector inside the submatrix. That's all what I'm saying. Like if you are in 3 dimensions, this coordinate axis would be the x-axis, because if you have a vector with 3 elements, the x element is the first one, then you have y and z. Okay. If it would be in 2 dimensions, it would also be the x-axis, because in 2 dimensions we have the vector x, y. So x is in the first place. That's what I mean. So it's as simple as that. We reflect it so that the vector now lies on the coordinate axis, and so it should make sense that if all other coordinates are 0, the first coordinate is the norm of the whole vector, because the vector is still the same vector. We just reflected it, but it's still the same physical quantity. So obviously this first element should be the norm of the whole vector, because we just moved this vector. It's still the same vector. I hope you see what I mean. If I take a book and change its position or whatever, it's still the same book. It still has the same volume or whatever. So it's still the same thing. That's why the norm of the old vector is in the first place and everything else is 0. So that's just a convenient way to store large data inside a computer or whatever is the use of this Householder transformation. So this is simply it is simple geometric, by the way. And also, where does this formula come from? We showed it in the first video. Also, you can find it on the internet. Just Google search for Householder transformation intuition. I said this Mr. Householder, the matrix is named after him. Yeah, use the properties of dot product, can be written in matrix multiplication. Yeah, the properties of reflection or whatever to build up this Householder transformation. You can look for the derivation online if you want. It's simple geometric. It's nothing complicated. I hope it was clear and that you understood it. Yeah. So I hope that's it. Thanks for watching, and yeah.